Hey there, Physics 126. Happy Monday, April the 13th, 2020. Um, let's start with a couple jokes. Let's see. Did you know you don't need a parachute to go skydiving? You need a parachute to go skydiving twice. Let's see if I can give you another one. Parallel lines have so much in common. It's a shame they'll never meet. If you have better jokes than that, and I'm sure you do, make sure to send them to me and I'll see if I can share them with you all. In any case, reminding ourselves where we've been, and it's useful to do that because we're starting today our last set of material that we're going to discuss between now and the end of the year. We started off talking about how things move with particles. We did kinematics. Then we did why things move, dynamics. From there, we then talked about forces, and we talked about then changing coordinate systems, rotational motion. We moved on and talked about systems where the forces weren't constant, and then finally generalized to many particle systems. First, where all the particles are traveling in the same direction together with fluids. And now we're going to start many particle systems where the objects are moving randomly in that limit. We'll talk about gases. So today, we're starting talking about many particle systems with random motion, in particular gases, temperature, and energy. As always, we'll have you start with some reading. Now remember, this material sort of winds together in different ways. It is hard to have it flow together really well, and books don't really put it together in a way that makes a lot of sense. So we're going to adjust around a little bit with the goal of trying to finish new material, hopefully by Friday, the 24th of April, so we can do some sort of review on the 27th, so we can have our exam for the 29th. So along those ends, I'd like you to read sections 18.2 through 18.5 of the book, 20.1, and 20.5. Now remember, we're not going to cover all this stuff in equal depth, and so you want to read this sympathetically to get an idea and be able to go back if you need to. But as you're reading it, I'd like you to think about how we measure temperature. What does temperature mean macroscopically? And what does temperature mean microscopically? Those are the things that we're after today. So here's where I ask you to pause, do your sympathetic looking at the text, and come on back when you're done. Okay, welcome back. So here are two thermometers. We have one on the left and one on the right. It's a mercury thermometer. The mercury is this silver liquid down at the bottom, and then there's this really thin little tube that allows the mercury to go up. As you put it in different materials, here in this case, the water in this tube is heated. As you put it from a low temperature at 20 degrees Celsius to a higher temperature at 30 degrees Celsius, the level of the mercury goes up and tells you that it's 30 degrees Celsius in here, whereas here it's only 20 degrees Celsius. Now the key point here, and I know this sounds really flippant, but in the end, it is our first best definition. Temperature is what a thermometer measures. And we're going to use that to try and understand eventually what temperature means microscopically. But we're going to start with this definition. Temperature is what a thermometer measures. Now, we can measure our temperature in a lot of different units. We can measure our temperature in Celsius units, where water freezes at 0 and boils at 100. We can measure, that's the C here for temperature C. We can measure our temperature in Fahrenheit, where water freezes at 32 Fahrenheit and boils at 212 Fahrenheit. We choose to measure our temperatures in an absolute temperature scale, Kelvin, where 0 Kelvin is the lowest temperature you can achieve at all, and then it rises from there. And the difference between Celsius and Kelvin is an additive constant of 273.15, where temperature Celsius is the temperature in Kelvin minus 273.15. So 0 Kelvin would be minus 273.15 Celsius. The key point here, we measure our temperatures in Kelvin always. Now your problems are going to give you temperatures in Celsius, certainly. Convert them to Kelvin no matter what. I will try hard never to give you problems where the temperatures are in Fahrenheit, because that's just English evil units. So let's ask a couple questions here then, or ask a question. So we have a pair of materials, and we want to know which one of these is twice as hot as the other. Boiling water at 100 and a glass of water at 50. Boiling water at 100 and frozen methane at minus 50. Notice these are in Celsius. An ice cube at minus 20 and flames from a circus fire eater at 233 Celsius, or none. Give you a second to think about that. Okay, got your answer? The answer is C. Now, it isn't A because these temperatures are in Celsius, yet we measure all our temperatures in, remember, Kelvin. And so this is 373 Kelvin and this is 323 Kelvin. They're not a factor of 2 of each other. This is 253 Kelvin and this is 506 Kelvin. And look, those are a factor of 2 from each other. So the point here being is that a factor of 2 in Kelvin is a big difference. Okay. Now, going back here, if temperature is what a thermometer measures, we can ask ourselves, well, how does this thermometer here measure temperature? And the reason, of course, is that this mercury expands as it gets warmer, and it expands upward, and that's why it goes to higher and higher levels, and we can measure different temperatures. We see this every day. For example, when we talk about expansion joints, here's an expansion joint in a road and a bridge. Here's an expansion joint in a building. As the temperature increases, the roadway expands, and so the two pieces come closer and closer together. If they were to come too close together, they would buckle up and destroy the road. So instead, what they do is they actually make them with teeth so that as they expand, they can just fit into each other and not buckle up. So if we're going to talk about why thermometers measure temperature, we have to talk about the fact that as we warm up, things expand. And that requires knowing that, well, if we look at any particular, let's say solid, we'll start with solids, they're the easiest thing. Remember, all systems that are bound and stable act as springs to zeroth order. So when they have each of our atoms that's connected by springs to another atom, which is connected by a spring to another atom, which is connected by a spring to another atom, and so on, so that these things can stretch as more energy is put in. And that all of a sudden now starts to make sense. As I put more energy in, then they're going to stretch. If they stretch, then this whole thing takes more volume. It expands. Here's an example then of how we think about that. This is a set of railroad tracks. You notice that right here, midway through the picture, the railroad tracks curve. The reason why is that the railroad tracks have tried to expand over time as they've warmed up. And so therefore the extra railroad length of the railroad ties, the railroad rails has to go somewhere, and it goes into a curve. The idea here is in this blue box. The actual expansion, delta L, well, what should that depend on? It should depend on the original length. It should depend on the temperature difference. If there's no temperature difference, something should stay the same length. If there is a large temperature difference, it should expand. If there's a much larger temperature difference, it should expand even more. Double the temperature difference, you should expect to double the expansion. And then finally, it should depend upon the material. Some materials should expand a lot. Some materials should only expand a little bit. And this alpha here, this coefficient of thermal expansion, it tells you about each material. Now your book does volume expansions as well. We're not going to do those. If you want to do a volume expansion, what would you do? You take the expansion, here we go, in one direction, alpha L times delta T. You take the expansion in the other direction, alpha times L times delta T. You take the expansion in the third direction, alpha times L times delta T. You figure out 3 new lengths, you get a new volume. Subtract that from the original volume, you get the change in volume. I'm not worried about that though. The key point here is depending upon the material, alpha, and depending on the initial length, L, as you change an object's temperature, it will expand or contract. You can measure this for bunches of materials. You notice here that something like lead and aluminum and copper and brass and bronze expand a lot. And things like glass or Pyrex don't expand much at all. I present this to you so that you can know that in your book, there is an expansion coefficient table should you need it later. So let's try an example. We've got a segment of railroad track. It's got a length of exactly 30 meters when the temperature is exactly 0 degrees Celsius. Cold day, freezing water. What's its length when the temperature is 40 degrees Celsius? Notice that's a temperature change of 40 Celsius from 0 to 40. A change of 40 degrees Celsius is also 40 Kelvin. And so therefore we can say that the change in length is alpha for steel. We'll have to look that up on the table, times the initial length, which is 30 meters, times the change in temperature, which is 40 to 0, 40 degrees Celsius. We can look up alpha for steel from the table. Alpha for steel is 11 times 10 to the minus 6. So 11 times 10 to the minus 6 times 30 times 40, 0.013 meters. Its final length will be its initial length plus that delta L, or 30.013. It should expand by a centimeter. What happens if it goes down to negative 40 Celsius? Well, if it goes up by 0.013 when it expands by 40, it'll go shorten by 0.013 when it goes down by 40 degrees. So we get to 22.987 meters. It'll shrink. So those are solids and liquids. Let's talk about gases, because that's where we're eventually going to be going. Now, the great news about gases is you already know the answer. You did this when you were in high school chemistry. PV equals nRT. The pressure on a gas times in a gas, of a gas, the pressure in here, times its volume, is N, the number of moles, times R, the gas constant, times T, the temperature. R is 8.314 joules per mole Kelvin. Notice the temperature is in Kelvin. N is the number of moles. B is the volume in cubic meters, and P is the pressure in newtons per square meter that we've been talking about. Now, one key thing here to note is that there are two ways to write this, I think, called the ideal gas law. We can write it the way chemists write it, PV equals nRT. Or if instead of counting number of moles, I decided to count the number of particles, N, the number of moles is N over Avogadro's number. And so this little n is the number of atoms over Avogadro's number. If we take the Avogadro's number and make it R over Avogadro's number, we get a different constant called K. And so we can write the ideal gas law either as PV equals nRT, the chemist's version, or we can write it as PV equals nKT, which would be the physicist's version. They're both exactly the same. There's no reason to prefer one over the other. Just that chemists like to count moles and physicists like to count numbers of particles. The only difference is on the right-hand side, instead of multiplying by R, we multiply by Boltzmann's constant, which is R over Na, which is 1.38 times 10 to the minus 23rd joules per Kelvin. Okay, so let's try a couple things. So we have what we do sometimes in packages is we trap bubbles of air between sheets of plastic. Is this material more effective at keeping the contents from moving around in the package on a hot day, a cold day, or either one? I'll let you come to your answer, and the answer is a hot day. As the temperature goes up, the stuff expands. That makes this air in the plastic bigger, which means that it pushes up against the sides of the box better, and so it's harder for things to move. Here's another one. On a cold day in your house, you turn on your furnace, and the temperature of the air inside your house increases. Now, houses aren't perfect. Air leaves the house. Is the number of moles of air in your room at a higher temperature bigger, smaller, or the same as when your house was cold? Your answer, think about it. Here we go. It is smaller. Why? Well, if air isn't going in or out actively, there's not like a wind eventually, the pressures on the inside and outside have to be the same. So the pressure is the same. The volume of your house is the same. It isn't like you made your house bigger. The temperature went up, which means that the number of moles has to go down to keep PV a constant. And so therefore there must be less total air in your house. Put another way, as the temperature went up, I pushed some of the air out of my house to the outside. Let's try a numerical example. By the way, don't do this at home. Please don't do this at home. A spray can containing propellant gas at twice atmospheric pressure and having a volume of 125 cubic centimeters is at 22 degrees Celsius. So we know the initial pressure, we know the initial volume, we know the initial temperature. It's tossed into an open fire. Bad. It will kill somebody if you do that. When the temperature of the gas in the can reaches 195 degrees Celsius, the temperature of a fire, what's the pressure in the can? Well, we know that PV equals nRT, and so that tells us that PV over T equals nR. We can use the initial information here to find the number of moles if we wanted to. We could also instead take a ratio, knowing that the number of moles stays the same. We could say that PV over T initially has to equal PV over T finally. Since the volumes are the same initially and finally, it's the same can. It means P over T initially equals P over T finally, or the final pressure is the final temperature, or the initial temperature times the initial pressure. Plugging in the numbers, we get 320 kilopascals, or roughly 3.2 times the Earth's atmospheric pressure. You can see why this is dangerous. I take a can, I throw it in a fire, I heat it up, the pressure increases, and eventually, boom, it explodes, and metal shrapnel's flying everywhere, hitting you and perhaps killing you. So at this point, we know that temperature is measured by thermometer. We know that temperature causes solids, liquids, and gases. An increase in temperature causes all three of those things to expand. Our real question, though, is why? We're physicists. We want to know why these things happen. So that requires taking a microscopic look at what's going on. So I'm going to lead you through a derivation here. I'm not going to ask you to do the derivation, but you should see it because the punchline is really cool. So what we imagine here is we have a gas. Here's a particle in our gas. Here it is. It hits the wall and bounces off. This could be a wall of a balloon or a building or something that the gas is in. Now, the change in momentum is it comes in with a negative momentum in the x direction. It leaves with a positive momentum in the x. The change in momentum is twice the initial momentum with an opposite sign. The force then is just the change in momentum over the change in time, or right here, the force is the change in momentum over the change in time. Now, the amount of time that we have is how far away this particle is, times 2, because it's going to hit and then come back, divided by the speed. In other words, v delta t is just twice of d. We put that in, then we get mv squared over d is the force. It's part 1. Part 2, well, if we want to figure out the force on the wall, it's just going to be the negative of that. Yay. But then we have to allow for the fact that there is more than just one particle in here. There are going to be n particles that are hitting the wall. So we have to add this up over all n particles. And so if we pull out the m naught and d, which are the same for all the particles, we just get F is m naught over d times the sum over all the particles of their speed in the x direction squared. Well, that expression here, we can realize if we had say that all particles are traveling at their average speed, then this would be n times the average speed squared, and that's what we have. Now, the last thing is that we can travel in 3 directions. And so on average, the speed in the x direction will be the same as the speed in the y, is the same as the speed in the z. And so that means that the speed in the x direction is 1/3 of the average speed squared. We get this factor 3 here from the Pythagorean theorem. So if we put in that the average speed in the x direction squared is 1/3 of the average speed squared, we get 1/3 times m, the number of particles, times m naught over d times the average speed squared. Now we can figure out the pressure. Pressure is force over area. That's force over d squared. So we take this force and divide it by d squared, so we get a d cubed in the bottom. That d cubed is a volume, though. So we get n over a volume times 1/3 m naught v squared. I like m naught v squared. That looks like an energy. So let's multiply this thing times 2/3. Let's multiply this thing time. Let's break this up into 1/3, 2/3, and 1/2. 2/3 out in front, and the 1/2 with the 1/2 m naught v squared. And so there's the pressure. 2/3 times the number of particles per volume times 1/2 m naught v squared. Okay. Last step. Let's multiply by v because we want to do PV equals something. Multiply by v gets rid of this volume down here in the bottom. And so we get PV is 2/3 n times 1/2 m naught v average squared. And if we compare that to PV equals nkt, this says that 1/2 m naught v squared has to be 3/2 kt, bringing the 2/3 to the other side. Okay. Why is that a big deal for us as physicists? Because our big physics point is this gives us a physics picture of what temperature means. This right here, 3/2 kt, is equal to 1/2 m naught v squared. I know what 1/2 m naught v squared is. That's the average kinetic energy of a gas particle. The temperature of a gas tells us the average kinetic energy of a gas particle. That's a useful physics point. And that's why we outline it here as a big physics point. Now, this part here, notice we won't test you on this, but that was assuming that particles, this 3/2 kt assumed that particles moved in all three directions. Since there's no differentiation between the x, y, and z directions, x, y, z, then that means that each three of these directions have to contribute equally to the kinetic energy. And so we come to this concept that each degree of freedom, x, y, and z, contributes 1/2 kt to the energy. So if I only moved in one direction, I'd have 1/2 kt. If I moved in two directions, I would have 1/2 plus 1/2 is 1 kt. And moving in three directions, I have 3/2 kt as my energy. If I had other directions like vibrational degrees of freedom or rotational degrees of freedom, I could get something like 5/2 or 7/2 kt. Now, if I want to know the total kinetic energy in a bundle of gas, then I'd have to take that energy in a single gas particle and multiply times by the number of gas particles. So I could take n times 1/2 mv squared, but we just said before the 1/2 mv squared was 3/2 kt. So n times that would be 3/2 times nkt, or if you prefer as a chemist point of view, 3/2 nRT. And boom, that's the total kinetic energy that I have inside a bundle of gas, inside a bundle of gas. That looks like I said it twice. Now we can talk about the gas in there. We can talk about, for example, the average speed or the RMS speed. RMS stands for root mean square. Read it backwards. Square the numbers, find the average, that's a mean, and take the square root. So it's the square root of the average of the squares of the speeds. We know what that is. The average of the squares of the speeds, divide by n, divide by m, multiplied by 2 is 3 kt over m, or square root of 3 RT over the total mass. So this allows us, if I had some volume of gas of air, I could figure out how fast the particles are moving around inside. And it turns out at 20 degrees Celsius, you're talking about temperatures, depending upon the mass of the stuff, between about 300 and 1900 meters per second. We're talking about oxygen hanging around, O2. We're talking about 478 meters per second of the oxygen molecules, would be the speed of the oxygen molecules in this room. Let's try a quiz. So we have two containers. They hold an ideal gas at the same temperature and the same pressure. They have the same type of gas. Container B has twice the volume of container A. How does the average translational kinetic energy per molecule compare? Your answer? Well, they got to be the same. Remember, the energy of a particle depends on the temperature. We saw the temperatures were the same, so therefore the translational kinetic energy of each particle must be the same. Let's try a different one. Same two containers, have an ideal gas, same temperature and pressure. Both containers contain the same type of gas, but the container B has twice the volume, so it's the same setup. What is the internal energy of the gas in container B? Slightly different. Get your answer. Here we go. Has to be twice. Remember, the volume of container B is twice, so it has twice as many air particles. If the energy of every air particle is the same, the energy in container B must be twice of container A. Let's try a numerical problem. Here, consider a tank full of helium. The whole tank has a volume of 0.3 cubic meters and contains 2 moles of helium gas at a temperature of 20 degrees Celsius. What's the total translational kinetic energy of the gas molecules? Notice in doing this, we're not asking for one, we're asking for all of them. Well, the total energy is 3/2 times the number of particles times kT, or 3/2 times the number of moles times RT. If we do the first one, it'd be 3/2 times 2 moles times 8.314, that's R, times 293.15, temperature in Kelvin. If we do the 3/2 nKT, it'd be 3/2 times 2 moles times Avogadro's number of particles per mole, times Boltzmann's constant, times 293.15. And no matter which way you do it, you get 7,310 joules of energy in that container due to the kinetic energy of the particles flying around. Making the point that either the chemist's way of looking at it or the physicist's way of looking at it give you the same answer. Let's try another problem. What's the average kinetic energy of a molecule? Well, that's just 1/2 mv squared. That's the same as 3/2 kT. That's 3/2 times Boltzmann's constant times T, 6.07 times 10 to the minus 21st joules. And what if the temperature was raised from 20 to 40? Would the translational energy be twice as large? Well, the answer is no. Why? Well, remember, we measure our temperatures in Kelvin, and the energy is proportional to the temperature. So the ratio of the energies will be the same as the ratio of the temperatures. 313 to 293, it'll only be 7% larger. So though we raise the temperature, we double the temperature in Celsius, we only raise the temperature by 7% in Kelvin, which means we only raise the energy by 7%. That's really the end of the material that you need to know. Further days will have less stuff, hopefully. There's one last thing to talk about just for you, and that has to deal with our buddy James Clerk Maxwell, also important in Maxwell's equations from E&M, smart guy. Notice down here in the bottom, won't test you on this. Point of James Clerk Maxwell is that he did a study and realized that not all particles in a gas are exactly the same speed. We made the assumption that they're all at the same speed, and that's not really true. In fact, if you look at the number of particles here on the y-axis as a function of their speed, there aren't very many at low speeds. There are a lot at intermediate speeds, and then decreasing numbers as you go to higher and higher speeds. In fact, you can get this distribution here, which I won't test you on. It's called the Maxwell-Boltzmann velocity distribution. This function, if you plug it in, will give you this curve. The reason for showing you this is we did the RMS speed. 3 squared of 3 kT over m. That's this value right here. You can also find the average speed. It's a slightly different number. It's the square root of 8 kT over pi m. You can find the most probable speed, which is the peak of this curve. That'd be the square root of 2 kT over pi m. The point here is when you're trying to discuss a gas where you have a distribution of speeds, you really have to use the distribution function. And there are a lot of different single numbers you can use that mean slightly different things. The RMS, most probable, the average will all sort of give you different numbers. The average speed is the average speed. The RMS speed is a measure of the average energy. The most probable speed tells you which one we most likely find. And so you have to be careful when you're trying to define these things and you're trying to use them. And so the note here is for future reference. Probably want to use the total distribution if you care about that level of detail. Finally, the last thing for you to see is if you take this distribution in temperature, distribution of speeds, and you increase the temperature, what happens? Well, if I increase the temperature, I give more kinetic energy. If I have more kinetic energy, then the RMS speed goes up, which means that this curve shifts to the right. Since there are the same number of particles, that means the total area has to be the same. So it shifts to the right, but then the peak has to come down. And so it gets, instead of being narrow, it gets lower and wider, just like we show here on this figure. So be aware that there's something called the Maxwell-Boltzmann distribution, and not every particle really is at the same speed. For our purposes, we will really assume that every particle is at the same speed, and use that to determine things like the energy that's inside, called the internal energy, and how that relates to the temperature. So again, reminder to yourself, what things do we have to know? Temperature is what a thermometer measures. We measure our temperatures in Kelvin. Temperatures cause things to expand according to this linear expansion coefficient, alpha L delta T. That expansion works not only for solids, but also works for gases. We can write PV equals nRT or PV equals nKT for the ideal gas law. And after a lot of work, this temperature T is directly related to the energy, the kinetic energy of individual gas particles, by the idea that the kinetic energy is 3/2 kT in an ideal gas. I hope you have a great day, and I look forward to talking to you later. Take care.